All right, it's 10:20. Let's go ahead and start. This is week 9, episode 16. So we're actually halfway through. Take note though, quiz number 14 and 15 will be doing tomorrow. Just don't forget about that. There's again no PA due this week. However, there's going to be a PA due next week. So PA number 7 is coming up. It's slightly complicated and it's actually getting into the core of the benefit of using Golang. So the second half of the lecture today is going to be mainly about PA 7. But the first hour, it's going to continue what we have left off yesterday, the example of go back in. We're halfway through and there's the other halfway. And now we come back to the sender side. Okay, we'll be receiving ACK0 here. All right, so receiving ACK0. It triggers sender finite state machines. Oh, the transition at the bottom, isn't it? Receiving a call from below. Yeah, receiving a feedback packet from below. Ooh, what do we do there? Yeah, let's recall and go back. Yeah, so here, quickly recall. Okay, this transition, getting a packet from the lower layer and it's not corrupted. What do we do? Set the base to the sequence number in the ACK packet plus 1. And then we check whether we need to stop timer or refresh the timer. Now, only when the base and the next seek num are equal, then we stop timer, because the base here is empty, meaning no yellow packets at all, because next seek number is the first blue. So only when the base and the next seek number are the same. Otherwise, restart timer. Okay. Now we can come back here to examine. Yeah, what is the action the sender should be taking? Okay. First, receiving ACK0. So that's triggering the transition at the bottom, a feedback coming from the lower layer, and it's not corrupted. So what we do is to extract the sequence number in the ACK, add it by 1, and that will be the new base. So base here is moved by 1 position. The next thing we do is to check whether the base equals the next seek num, right? If they are the same, that means we should stop the timer, because hey, all the data packets are already added, right? But otherwise, then we restart the timer. So hey, base is 1, next seek num was previously 4, isn't it? That's why we are waiting here. Okay, so we cannot be stopping the timer. Instead, we should what? Restart the timer. So this timer here, original ticking, will be canceled and we restart the timer here. And that timer is going to be associated with the new base, which is 1 over here. All right. And then, hey, sender is trying to send data. So quickly get a call from above. So we trigger the top transition. So next seek num is 4, and 4, is it less than the base 1 plus the window size 4? So together 5. 4 less than 5. Cool. We can generate packet 4 and send it out. Is the sequence number base equaling the next seek num? No, so we do not start timer here. All right, so base is 1, so that means base, there's already a timer running. All right. Next seek num, 4, not equaling 1. So not starting a timer here for generating packet 4. So timer is still associated with the base 1. All right. And then we increment the sequence number by 1. So 5 here. Okay. Similarly, receiving ACK1. We set the base to 1 plus 1. So the base is now what? 2. Is the base identical with the next seek num, which is 5? No. Therefore, we do not stop timer. But instead, we restart timer. So T removed there. And T is restarted with the new base. That is 2 over here. Okay, so T for 2. So this is T for 1 and this is T for 0. And at this point, one slot open up, getting called from above. Yeah, 5 is less than 2 plus 4, 6. Therefore, we generate packet 5 and send it down. And do we start the timer? No, right? And increment the sequence number to 6. And yeah, another ACK 1 is coming in. Okay, this is triggered by receiving packet 3 without packet 2. So ACK 1 comes in, triggering the bottom transition, not corrupted, set the base to 1 plus 1, 2. Well, that is the same. All right. Base and next seek number, still not matching. Therefore, we restart timer. Ooh, so, hey, we actually killed the old timer for base 2. Now, restart timer for base 2. That means, wow, this base is actually, waiting a longer time to expire to retransmit. But it's okay. It will still work. Just wait a bit longer. Right. If we get a call from above now, next seek is 6, and base is 2. 2 plus 4, also 6. 6 not greater than 6. Therefore, we again wait here. All right? So, yep, pretty much wait here. And so this timer for the base 2 is going to tick, 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 tick. All right. Let's assume packet 4 and 5 arrive at the receiver side, which generates react of packet 1 because they are out of order. And let's just assume these two acts is just going to take a long time to come back before T4 2, the second time here, times out. Okay. What's going to happen here is that it's going to trigger the sender side, the timeout event. What do we do there? We restart timer and what? Retransmit the entire flight of packets starting from the base. So 2, 3, 4, 5 go out at once. All right. And good thing is that at the other end, the receiver here finally gets packet 2. Yeah, it's finally the expected sequence number, so it's going to call the transition on the right, extract data, pass it up, so deliver to the application layer, and therefore we generate Act 2. And packet 3 arriving here, extract data, and then generate Act 3, and so on and so forth. And so that was the other half of the go backend example. Now we move on to the second big category called the selective repeat. Selective repeat. This is the second big category of the pipeline RDT. So its design is pretty much the opposite of go backend. So in go backend you have cumulative acts. So the sequence number in the act there is to indicate all the packets before these particular numbers are received correctly. But in selective repeat, the acknowledgements are individual. So one acknowledgement packet per data packet. The sequence number in the acknowledgement is only to acknowledge one data packet. In go backend, we have one timer for an entire flight of packets. When that timer times out, we retransmit the whole flight of packets. In selective repeat, the opposite. We have one timer per data packet. When that timer times out, we retransmit just that data packet. All right? So, receiver will acknowledge each correctly received data packet individually. Sender will only retransmit a packet when the timer for that packet expires. Very straightforward. The slight tricky part of the selective repeat is at the receiver. Okay, we now have to buffer packets arriving out of order. The reason for this is very straightforward, very simple. If we send packet 1, 2, 3, and 1 arrived at the receiver, 2 get lost, 3 arrived at the receiver. You cannot be just extracting the data bits out of packet 1, pass it up to the upper layer, and not passing the bits of packet 2, and immediately pass the data bits in packet 3, and then later pass the data bits in packet 2, because that way you get bit sequences that is out of order at the application layer. And our definition of RDT is that all the bits arrive reliably and in order. So, receiver here in selective repeat, the implementation gets complicated. You need memory space to store temporarily the packets arriving out of order. And you wait until all the gaps are filled, and then you pass all the data bits up to the application layer in sequence. The only thing that remains the same is there is still this sending window, which is limited by n, from the base to base plus n. Now, be a bit careful in selective repeat though. What we are limiting there is the sequence number of the unact packet. So what is the maximum sequence number there can be unact. As opposed to in go back n, we say n being the number of unact packets. The reason that I'm saying you need to be careful is because of this. From the base to n plus base. Yeah, there are yellow packets, alright, and after the yellow packets, the blue packets. In go back n, they're just gonna be yellow and blue. So the number of yellow packets maximum will be n. In selective repeat, because we have individual acts, so some of the yellow packets can be green, like this. Alright. So even though they're turned green, but that doesn't mean that they will include these 4, okay, into the window, like this. Okay, no. So what we're restricting is the maximum sequence number that can be unact, not the maximum number of packets can be unact. Okay, just to make sure that's clear. And the receiver of selective repeat is, as we talked about, more complicated. It also maintains a certain data structure, tracking the status of these packets. So we also have a window size here at the receiver. The base is now called the receive base. So receive base is always pointing at the first packet expected but not yet received. Right? And there could be a number of these pink packets around. So these are the packets arriving okay, but out of order because there's a gap before it. So those are the out of order buffered packets. The blue ones are reasonable, okay, packets that are expected next. Okay. The black ones are just not possible. So if we receive packets after receive base plus n, we'll be just treating these as maybe hackers injected packets, spoofed packets, things like that. And now the selective repeats finite state machines. This is the sender side of the machine, and this is the receiver side of the machine. And you might be going, wait, they don't look like FSM at all, right? Because previously we have like states, right? And the number of transitions like these. Yeah. What I'm doing here is to do textual representation. So what I'm saying is essentially, yeah, there are still 3 transitions. So first transition is triggered by this event, the data from above. Okay. Second, the timeout event. Third, triggered by receiving an acknowledgement packet within a particular range. So later on, you will see what's nice about writing the finite state machine this way, because it looks almost like a pseudocode, isn't it? right? So the sender side is looking like a switch procedure where when there's the data from above event switching in, then we do this. When there's the ACK packet being received switching in, then we do that. So now let's go over the finite state machines of the senders and receivers. Sender side, when there's a call from above, okay, if the next available sequence number is within the window, yeah, send packet. And you know how to do the next available sequence number, whether it's in window check, right? So the next seq num should be less than base plus n. Second is a timeout event. If our timer times out, and that is for packet sequence number n, we retransmit packet n and restart timer. Straightforward. If we receive an acknowledgement packet, we extract the sequence number and check if it's within the send base and send base plus n subtracting 1. So that is saying, hey, whether the ACK is within the reasonable range, right? Because the send window is only this big. If we receive ACK before that or after that, that's just weird. Okay, let's just ignore those. So we'll only be handling ACKs that's within the send window. Now, once that's the case, we mark packet n being received, so turn it to green. If n smallest unACK packet, so if n here is also the smallest unACK packet, so we turn that into green. There could be a number of other greens following that. Then we could what? Advance the send base all the way to the next yellow packet. Okay, so advance the window base to the next yellow packet, which is the next unACK packet. All right. So this is sender's actions depending on what's triggering the sender's finite machine to take transitions. Similarly here at the receiver end, there are 1, 2, 3 transitions. First transition is if we receive a data packet that's within this range, the receive base and receive base plus n minus 1. So that is reasonable, okay, as expected. Then we send individual acknowledgement. So if it's packet n, then ACK n. If this packet is not expected, so meaning it's out of order, then we will buffer them. So these will be the pink packet, all right? Now, if this packet is actually coming in and filling one of the gray packet, so unreceived previously but expected, then we can pass all the packets suddenly in sequence, all in pink, up to the application layer. So that's deliver those, okay, in ordered, and advance the window to the next, not yet received, but expected packet. So to the next gray packet. All right, so this is when we receive a data packet that is within the receiving window. If we get a packet, okay, that comes in, but it's actually in this range, receive base minus n to receive base minus 1. What is this? Okay. We are actually sending an ACK for that packet back. If you recall, it could happen, right? The ACK packet going back to the data center, if that packet is corrupted, the sender there is going to wait until the timer for that packet times out, then retransmit the data again. But that data has already been arrived at the receiver previously. And that's why the receiver sends an ACK back to the data at the first place. And that's before the data is found corrupted at the sender as well. Right? So in that case, we still need to send the ACK for that packet. Okay, do not ignore this. Otherwise, that timer is gonna fire it again and again, and the sender there is gonna retransmit the same packet again and again and again. Right? Third transition, otherwise, or the default, I'll just ignore. Okay, so receiver pretty much do nothing in case it's packet not within the receiving window or not one receiving window before. All right. So those that are outside, just ignore it because chances high that they're coming from hackers or previous connections, and the data somehow, the packet somehow gets stuck in the network for too long, and it's gonna be useless anyway. All right, so that was general idea of selective repeat. Let's go over also an example and talk about finally the relationship between the window size and the sequence number. And that's also walk through an example of selective repeat, just like we did one for go back in. So that example in go back in is actually harder to analyze. This one, on the other hand, relatively easy. Now it looks very much like the example in go back in. So window size 4, and we start from base 0 and the next seek number 0. Getting a call from above? Yeah, because the next seek is less than base plus 4. Therefore, we generate packet 0 and send it out. And we go on until we hit next C equals 4. And that is not smaller than 0 plus 4 anymore, so we wait. All right. Now, over at the receiver side, scenario similar, receiving packet 0, but the receiver's action different. Okay, for packet 0, we send individual ACK 0. Receiving packet 1, we send individual ACK 1. Well, not getting packet 2, but we'll be getting packet 3. And out of order, so we buffer and send individual ACK packet, ACK 3. So ACK 1, ACK 0, ACK 1, and ACK 3 will go back to the sender. Now, sender, upon generating packet 0, packet 1, packet 2, and packet 3 will all start the timer individually. So T0, T1, T2, and T3 will all be ticking, no worries. Okay. Now, ACK 0 now comes back to the sender. Sender receiving ACK 0 will do what? Clear packet 0. So that packet will turn green. All right. Is it in sequence? Yes. So we advance window. Yeah. Advance window by 1 to the next unacked packet. Upon receiving packet 1, also, advance sequence by 1 because it's in sequence. And hey, so base is changed to 1 and then to 2. So that allows us to send packets more, right? So 4 is generated, 5 is generated, and they're being sent out. Well, packet 2 did not get acknowledgement, but we get what? ACK for 3. All right. So what do we do there? Yes, we actually release packet 3. So we turn that into green. But hey, packet 2 there is still yellow. All right, so this green packet, packet 3, is not the smallest unacked packet. So we cannot advance the window size further. We cannot advance the send window further or the base further. All right, so cannot be sending more. So still wait here. Okay, so this part of go back in and selective repeat similar. Right? But now, look, packet 4 and 5 will go to the receiver. Receiver here receiving 4, out of order again, buffer, send ACK 4. Packet 5, buffer again, send ACK 5. And those will go back. Here, timer for 4, timer for 5 will be fired because there's one timer for individual packets. Okay. So finally at this time point, timer for 2 finally expires, and therefore we resend packet 2. Packet 2 goes out, received. Finally, this is the smallest unacked packet, and all the packets subsequenting packet 2, 3, 4, 5 can be passed up, okay, in sequence to the application layer. and we send back ACK for 2. All right. So, simpler. The last bit of selective repeat is this. Let me show you this case. There are 2 scenarios, okay? But from the reviewer's point of view, they will actually look the same, right? And this is due to the fact that the sequence number here, the sequence number space, and the window size there is not set in a way that we could tell individual packets apart. Those who are sent earlier versus those who are sent recently. Okay, so the example goes, sequence number, only 2 bits, so there are only 4 different numbers. Window size, 3. Right. So the selective repeat sender side will look like this. Well, the window size is 3, so we can only send 3 packets back to back of each other. So packet 0, packet 1, packet 2 goes out. Receiver here receiving 0, 1, and 2. They will then send back ACK 0, ACK 1, and ACK 2. So ACK 0 here arrives back at the sender first. And this is in sequence, so we advance the send base. And we generate yet another packet to go. All right. And the next ACK, that's going to advance the send base further to 2. Right? And we generate yet another packet to send. And the next one will be what? Yeah, carrying sequence number 0. Now, if packet number 3 did not arrive at the receiver, all right, receiver here will see, all right, I got a packet 0. And you know what? Within my window, I am indeed expecting someone carrying sequence number 0. So this one will be what? Buffered. And an ACK of 0 being sent back to the sender, isn't it? All right. So that seems to be fine. Yeah, this is the no problem case. Wait until you see the next one. Here's the next one. Same scenario, window size only 3, and we have sequence numbers. There are only 4 of them. So we send packet 0, 1, and 2 out. Receiver here generates ACK 0, ACK 1, and ACK 2 back. But unfortunately, all of them are lost. So timeout is going to happen and retransmit packet 0. This packet 0 will go, and receiver here will say, hey, you know what? I'm expecting packet 0. It's within the receive window. So buffer and send back ACK for 0. Sounds familiar, isn't it? Because that's exactly what's being done here in the first scenario. So from the receiver's point of view, identical. Also, buffer the packet and send back ACK 0. But the thing is this, at the sender side, you see, this packet 0 is a retransmission of the first packet 0. But this packet 0 here is actually the second packet 0, no longer the original, the first packet 0. All right. So if packet 3 here arrived at the sender, the sender is going to what? Clear that gap and pass 0 up to the application layer. Before that, pass, of course, packet 3's bits into the application layer. So 3 and 0's data bits will go to the application layer. But look here. This is packet 0. When packet 3 finally comes here, it's going to clear and send packet 3's bits as well as this retransmission 0's bits up to the what? The application layer. So you get unwanted duplicates. So you do have a situation here. From a receiver's point of view, it actually sees no differences in the two scenarios. You get duplicate data in the end in case B. So we need to be careful here to prevent, packet 0 here and packet 0 here obviously are two different packets, but being confused as the same packet. Okay, so according to case A, we'll actually pass packet 0, these bits again to the application layer. Not good. All right. So in order to tell this packet 0 and this packet 0 apart, we have to think, what is the worst case? Okay, can we use a sequence number such that we will not be confusing this packet from this packet? Okay, so a new packet should be farther away, should be carrying a sequence number that's farther away from an earlier packet. And no worries, if you look at this, case number 2, case B here, is already the worst case that I'm illustrating. So in this case, we're seeing that the receiver is advancing the receiving window one after another. So receiver is saying, hey, everything is okay, let's move on. But sending side here, not getting any X back, hesitates and waits and waits and waits and not moving. So you have one end moving really fast and the other end staying. Okay? So you see in the end, the worst case is what? The sending window never really moved, but the receiving window moved the entire end. All right? So they're actually end apart. If you want to make sure that none of the packets still in the sending window will be confused with the packets in the receiving window, what do you need to do? Isn't it obvious? The sequence number, make sure that the space is larger than 2 window sides, right? Then, hey, packet sequence 1 will never appear again in the next window, in the receiver's window. All right, so you would never have the trouble of confusing an old packet from a new packet. And that is why the sequence number space here needs to be larger or equal to 2 times the window size. And that is selective repeat. We start with a quiz summarizing the differences between the go back N and selective repeat. So Q16 here is asking, first of all, which method, so between go back N and selective repeat, which one uses more network bandwidth to retransmit in case there's loss? Okay, which one? Q2 here asks, which one of these tend to require more memory space at the receiver side? At the sender side, they all have to keep these windows of packets that are sending flights, not yet act. But at the receiver side, does go back N require memory space to store packets arriving? Does selective repeat require the receiver to store the packets arriving? Q3, which one tends to require more timers at the sender side? Oh, go back N requires what? A timer for a flight of packet, but selective repeat requires what? 1 timer per packet. So which one then ended up having more timers at the sender end? Q4, okay, so this is slightly more open. If you are to program a pipeline RDT, okay, and hopefully doing it with minimum effort, which method would you choose to implement and why? Would you prefer to implement go back N or would you prefer to implement selective repeat? So, you have 3 minutes of time to think it through. Okay, selective repeat versus go back N. Yeah, I know. Some of the cues are easier than the other. Bandwidth-wise, which one consumes more? Memory space-wise, which one consumes more? Number of timers-wise, which one requires more? So team 2 actually prefers selective repeat. Because it requires less bandwidth to retransmit, right? So if the minimum effort is minimum effort for the network, yeah. And team 4 is saying, okay, if one needs to implement the senders and the receivers, one will need to maintain multiple timers. Okay, so your argument here, team 4, is very similar to team 1's. In team 5, team 5 prefers go back in. I see. Yeah, so yeah, again, the part 4 there, Q4, is a little bit more subjective. So one will prefer one way versus the other. Good. Now, and that's also take advantage of the break to address the question earlier by, oh yeah, so Kevin was asking, oh, what if sender receive a corrupted ACK packet? Yeah, so in selective repeat as well as in go back and sender, when there's a corrupted feedback packet, what we do is just do nothing. So we wait for timeout essentially. Okay, so that is just to clarify. So the sender side of selective repeat there, that box, the pseudocode, should have one more entry that says default or everything else, okay, will be then to ignore. All right, so now let's move on to the next section, section 3.5. That's where we begin to talk about TCP's reliable data transfer. But in that section, we're going to talk a little bit more about TCP's other mechanisms to support reliable data transfer. And this is 3.5, connection-oriented transport, particularly the TCP protocol. So in this particular section, we're definitely going to talk about the RDT implemented in TCP. Now, provided the background, okay, very extensively in 3.4, you should be able to understand TCP's implementation of RDT, TCP's design of RDT. Now, in addition to the RDT in TCP, we are also going to talk about the packet format of TCP. And that is what the segment structure meant here by the textbook authors. And then there are two minor functions, but necessary functions in TCP. One is called the flow control. The other is called the connection management. And this is the overview. TCP we know already. Just like UDP, it's what? End-to-end process-process communication. So end-to-end there can also be referred to as point-to-point communication. We have a sender process and a receiver process. Now, in this connection here, what we're doing is to do reliable and in-order data transmission. Now, what's a little bit unusual when we talk about TCP is this. Instead of earlier, when we were talking about the general principles of RDT, we are counting the data by what? Packets. Packet 0, packet 1, packet 2, packet 3, so on and so forth. But in TCP, we count data all right, but we count the data by the bytes. Byte 0, byte 1, byte 2, and so on and so forth. So that connection here, when we are passing data around, we are actually passing a stream of these bytes. Right? So there's no more message boundaries, or there's no more packet-to-packet separation. Right? And last, this is actually telling you ahead of time that TCP's reliable data transfer is doing this, the pipeline-based RDT, so that we have a window size there where the size n is definitely larger than 2. And so we could have multiple packets in transit so that the utilization of the connection there can be higher. Okay. Now, what we don't know quite yet is this window size is also used not just for reliable data transfer. Later on in section 3.6 and 3.7, you will also hear it's also for the congestion and flow control. Okay, so there's going to be a window size for flow control, and the window size for RDT is also used, okay, for congestion control. And conveniently, in flow control, what's being done is the receiver will every now and then tell the sender, hey, you might want to slow down or you might want to speed up depending on how much the buffer space is occupied at the receiver side. You see, what happened at the receiver end of the TCP is this. Data will come in continuously from the sender. Data will be extracted and passed up to the application layer process. So there's an incoming rate and there's also an outgoing rate. When the outgoing rate is slow, incoming rate is fast, then you see the buffer space is quickly exhausted. Okay, so at that point, receiver tells the sender, hey guys, slow down. All right. Now, the other way around, if the buffer space is very empty, then telling the sender, feel free to send more. So full control there. Okay, mainly allowing the receiver to tell the sender, hey, slow down or speed up, such that there's no congestion occurring at the receiver side. Because if the incoming rate is high, outgoing rate is slow, over time, when the buffer is exhausted, the incoming packet, incoming data will be what? Will be dropped. Okay, so delay long, and you see also data loss there, right there at the receiver. So this is to avoid also congestion, but it's a bit weird. It's actually to avoid congestion at the receiver side, not quite in the middle of the internet. Okay, so when I say in the middle of the internet, I actually meant congestion in the core of the internet. Sender process, receiver process is what? At the end of the internet, at the edge of the internet. So flow control there is to try to control the end processes such that there's no packet drop at either end. Congestion control, on the other hand, is to control such that there's no packet drop or congestion in the middle, in the core of the internet. And TCP being connection-oriented transport layer service is sending some messages at the beginning before data can be transmitted. So there are some handshaking being done right before the data exchange. And these handshaking messages are there to set up the initial states of the sender and receiver. And that is called the connection management part of TCP. Last but not the least, there's a mindset change here in a TCP connection. Data traveling in a TCP connection is now full duplex. What I meant by that is the data flow is going, bidirectional. Okay, so two processes or point-to-points, will be sending data this way as well as this way. Now, why is this a major mindset change? If you recall in 3.4, when we were talking about these reliable data transfer mechanisms, we always say what? This is the sender side of RDT, and this is the receiver side of RDT. What we are saying there implicitly is also, this is data sender side of RDT. This is the data receiver side of the RDT. Data receiver there, receive data. It transmits something as well, but it's transmitting only what? The feedback messages, the ACMEX messages. The receiver there does not send data. So TCP here you see being more general. Data can go either way. So the two processes will be implementing both the sender and receiver finite state machines. And the last bit is this. MSS, a special term that is referring to this, the maximum segment size. If you recall, a packet at the transport layer is called a segment. So maximum segment size is essentially the maximum packet size. Okay. In reality, in actual TCP implementation, we're still sending data packet by packet. But the sequence number we'll be checking to do reliable data transfer is now counting the bytes of the data, not the packet numbers of the data. And so that's all for the overview of TCP. We'll continue discussion of TCP's reliable data transfer next Wednesday. And let's take a break. After we resume the lecture, it's all going to be about PA7. Which is to implement a half-baked web file server. Okay. So starting now, it's 11:09. We'll resume 11:19. So I put up again quiz 16. So those who wish to complete quiz 16, feel free to spend some time and type your answer up. Okay, it's 11:19. Let's try to resume the lecture. And yeah, as I have pre-broadcasted about the PAs. So in PA7, there are going to be two approaches that you can choose to take. Okay, it's not necessary that you choose a particular one. Approach one here is the one that requires more exploration, which equates to taking more time. So see how much time you have. You might want to take approach 2 first, so that at least you have a working PA7.go. And if you find that it's particularly interesting to explore more about Golan's web file server, then go ahead and take approach 1. Now, approach 2 is very straightforward as opposed to approach 1. more complicated, but complicated in a way that you need to read through some of the source code in Golan's web file server. So let's go ahead and start. This is the PA7. And first of all, congratulations for clearing the stage 1. If you think about it, it's a pretty long way, right? So there are 6 assignments and you're turning 1 each week. Quite intensive. And the first paragraph here I have are just a couple words of encouragement so that it motivates you a little bit to continue on into the stage 2. And stage 2 is composed of 3 assignments, PA7 to PA9. So it's also formulated as a series. In the end of the series, the hope is that you implement a very simple web server that allows secure downloading of text-based or HTML-based objects. To be more specific, PA7 here is an HTTP request interpreter. Okay, so the role of a web server is first to receive HTTP request messages. So the server there, after receiving the requests, we need to interpret the requests. PA8 here then extends the web server a little bit further so that based on the understanding of the HTTP request, we generate the corresponding HTTP response and then transmit it back. PA9 is to extend PA8 further such that the receiving and the transmission of the request messages as well as response messages will be securely encrypted. And allow me to add more here so that you see the real challenges ahead in stage 2. So first of all, back in stage 1, throughout PA1 to 6, what we ended up implementing is a file upload service. In stage 2, I just said that we need to implement a web server so that we could securely download these HTML objects. That is essentially a file download service. You're perfectly right. What is so challenging about implementing the file download service when we know how to do file upload already? So, implementing the functionality of downloading the files is not the challenging part. So the real challenge is this. Back in stage 1, we're implementing our own file upload client and our own file upload server. So the descriptions for PA3 and 4 there are essentially defining our own file upload protocol. It's very simple, isn't it? Sending the file size first as a number, and then the file follows. In stage 2, the real challenge is not to define our own web protocol, not to use our own web client. We'll be using the existing well-known web protocol, the HTTP. And we'll be using the existing web clients, which are all these web browsers. Okay, Chrome, Firefox, IE, Safari, or even the Unix command line curl, the curl command. Okay, so we'll be implementing a web server that can interoperate with all these web clients seamlessly. So the real challenge is this. The web server here, you as a programmer needs to understand the HTTP request messages. So you program the web server such that the web server understands the HTTP request messages. You as the programmer needs to understand the HTTP response messages so that your web server there can generate the HTTP response messages so that after transmitting them, the web browsers that people are using every day coming from different companies can understand and render the objects that you are allowing them to download correctly on the display. Now back to the description. So in each assignment in stage 2, you'll be seeing that there are different ways of implementing it to come to the same result. Now many of you might be implementing the web server using the socket APIs, which are these listen, dial, or accept APIs that are already defined in the net package. You'll be also learning these web APIs. So these will be new to you. They are the APIs defined in this package called the net/http. So net/http there is an extension of the net package, such that some of these HTTP protocol-specific actions or specific message formats are already implemented. So for those who like to do low-level, system-level programming, okay, and looking forward to a career of being a network or system software engineer, then feel free. Definitely use the native socket APIs. So minimum sets of APIs to implement rich functionality web server. Okay. But those who find application level programming more interesting and you're looking more into developing higher level apps, then definitely try out the new web APIs defined in net/http. But in either case, you'll be definitely Googling, trying, failing a lot more at this stage. The reason for that is because HTTP protocol is actually big. Ways to implement, you see the range pretty wide, right? You could use low level package or higher level package, and there's actually a pretty big space in between. So there'll be more trying and seeing what is the best for you, all right? So, but no worry, okay, you'll be also allowed more time to explore at this stage. So you see that PA7, it's only to be turned in 2 weeks after the midterm. Okay, and you see PA8 and PA9, each will be also allowed 2 weeks to work on, one after another. I know, some of you might be going, oh no. Yeah, chances high that you will start the assignment 1 day before it's due. I understand, okay? Try to think of it this way. Okay, the work is gonna be done anyway, right? Sooner or later. And the amount of work is pretty much the same. If you start too late, there's a chance of missing out on the due time. But if you start early, yeah, you get it done. And not missing the due date. It's actually quite straightforward. All right, so yeah. The purpose of college education is not only to build your knowledge base, but also to allow exploration, if you notice. You will not be only exploring ways to implement your assignments, but also to explore yourself. So hopefully, before you graduate, you learn that time management is an essential life skill. And now the real assignment. So what you're asked to do is to implement PA7.go such that it works like a half-baked web server, okay, that allows text HTML-based file download. So what you need to do is to receive and interpret these HTTP request messages, okay, and then just print the file size on the screen of the server, okay, not to send any responses back to the client yet. So more specifically, your PA7.go should do these. First, listens at the port number until there is an HTTP request. So reads the request from the socket and finds the path and the name of the file to be downloaded. Now, in case the file exists, so look for it in the file system. If it exists, print the file size on the server screen. Well, if the file doesn't exist, then print this, file not found, on the screen. All right. Close the connection and go back to, step 1. So this server here still needs to be a looping server. All right. Now, whether you like it to do concurrency or not, that is your choice. Okay. So all I'm asking you to do is to take one HTTP request at a time. Look for the path and the file name in the HTTP requests. And then checking the file system whether the file exists or not. If it does, print file size. If not, simply print file not found. And then go back to wait for another request. Let me share with you 2 examples that's going to lead you taking 2 different approaches. The first one is actually the high-level app programming style, where we include high-level packages. So more APIs available that we could use, pick and choose. Second one then is the lower level one. Okay, so using minimum sets of APIs and try to implement the same thing. And the first example is called the HTTP request as a request. Okay, so second request here is in different font and having a slight shadow in the background. So that is pollys notation of indicating that that word here is a special word being used in a program or a special keyword in the Golang language. So request here, capital R, is in fact a data structure that's defined in the net/HTTP package. We'll talk about it a bit more in the code walkthrough. Let's now start a file, the simple-request.go. Okay, simple-request.go. Let's copy and paste the whole block of code there, okay, and then begin to try it out. First is to replace your port number with the, of course, port number assigned to your team. And then let's go. Go run simple request.go. So the server is going to be running there on the same machine. Start a Chrome or Firefox or whatever browser you prefer. And then request to this URL, 127.0.0.1. Okay, and change the port number again. All right, so this is where the server is sitting. Okay, so you are asking the web browser to fetch a file from the server you just started. Alternatively, so Poly is going to use the curl, the Unix command line, to make it look a bit simple. All right, so I'm just going to curl, this object here. So curl 127.0.0.1 and then the port number. Okay. Quickly you will see, okay, curl responded that, hey, there's nothing coming back from the server. Yeah, the server there you are copying, the simple request.go, is actually only showing, hey, what's inside the HTTP request message, and it's not sending anything back. Okay, so client will not be receiving anything. Okay, so client will just stop here. Okay. Now, if you're using a web browser, a regular web browser, you might see that it's displayed on the web browser saying some sort of error. For example, the server refuses to connect, or the server is not sending anything back. That's normal because the server, the simple request.go there, is definitely not working like an HTTP server, right? But what's more important is when you come back to the server's terminal, okay, you see after the launching server ... method is what? Get, capital G-E-T. Yeah, that is the request messages command. And, okay, so the host, the server host is indeed, on the local machine and the port number assigned for your server. Okay. And user agent here is curl 7.64.1, which is the curl command that I'm using here. Now let's give it a try. So Poly is already in the PA7 directory and have the simple request.go, all the examples ready in the directory. So let's go ahead and execute simple request.go. All right, so server launched. And over here, we'll just, curl to the local machine. And Poly's server is always 11999 here. And requesting the home directory of the server process that's running. All right, so let's see. There we go. Port number out of range. Okay, this is one more 9 too many. Okay, so that's, reduce that to 11999. There we go. Okay. So curl says error message 52, empty reply from server. And over at the server side of the terminal, we see the server here prints the comment of the HTTP request received and prints the host header line in the HTTP request message received and the user agent header line content in the HTTP request received. back to the code. So first line, familiar. Actually, the first 3 packages, yeah, we've seen these in the first stage of PAs. And we are now importing a new package, net/http. So this is the function to check errors. So we know about this one already. Main function starts here. All right, so this is printing the line saying that the server is starting. Yeah, these lines also look familiar, right? So this is where the socket, the listening socket is started. Deferring of the listening socket. This is where the data socket is started, okay? So we could accept messages or send messages using this socket. This is deferring of the data socket, all right? Oh, reader. Okay, so this is a result of buff.io new reader. So we actually wrap around the data socket with the reader. So we could read strings. Nice. But instead of calling restring, what we're doing now is very special, right? We're saying http.rerequest. All right, so reader is right here, okay? So previously we call reader restring, okay? But now we do reader http.rerequest. So http.rerequest, there is an API defined in the net/http package. So this API actually works with the standard buff.io package that reads the text coming in from the reader, okay, it's a buff.io, and then what? Process it and store it into a request object. So request there is capital R, request data structure object. Okay, so REQ here is the variable storing the request object. Second value returned by HTTP request is just the error message. Right, so now with the REQ here, what we can do is to do this. So REQ.method. So defining the request data structure there. Method is a variable inside the data structure. So by calling REQ.method, we refer to the comment, okay, in the HTTP request messages received. Another variable in the data structure is the host. Okay, so this is the server host. So request.host refers to the value of the host header line. But to refer to the value of the user agent header line, there is a special API, user agent. So that is a function call. So this function call is associated with the request object. So in the struct there, defining the request object, there's a function as well, user agent. Okay, and calling this function gives us the value of the user agent header line. And I know what you're thinking now. So provided the REQ variable, how do I access the path and the file name of the object to be downloaded so that I can find out the size of the object? Very good. The pollys show you how poly explores the source code of net/http to find out how to access the method, how to access the user agent header lines value. All right, so next is the exploration process. As mentioned, net/http is the package where Golang defines all these HTTP related data structure, the APIs, as well as a full-fledged implementation of a web file server already. Okay. So this is very unusual for any programming language these days. So you could see the emphasis of Golang trying to do this. It is to enable fast and efficient development of internet applications. The source code of the package is entirely open, so it's actually right here at this URL. All right, but it's not recommended that you dig into the source code right away, okay, not knowing much about the package. So usually the easiest way is to start from an example, learning the APIs that's commonly used, learning the data structure that is commonly used first, and then gradually expand, right? And that is why we're starting from an example here. So buff.io new reader, okay, calling the socket that we just created. That converts the socket into a buff.io so that we could call really nice APIs such as restring, reword to take in text input. So one could definitely move on reading strings, reading words based on your knowledge of HTTP request formats and start parsing the HTTP request messages for yourself. But the other way around is to do this. http.rerequest. Okay, so this is a special buff.io API that allows you to read from the socket and parse the text in there, assuming it's a HTTP request, and store it as a request. Okay, and this is capital R here, request object, and that is already well defined in the package. So it's a special structure there, okay, defined in the net/HTTP package. What is a bit unusual is this, re-request as an API, it's actually defined in the net/HTTP package as opposed to in the buff.io package. So you see this is a very HTTP specific API, although it's defined for the reader buff.ios. Now think, if re-request they're already done the parsing for you, and the output is stored as the request object, the capital R request object, all you need to do seems to be to understand the data structure of the request object, right? Then you can go to the URL field. That's where the path and the file names is stored. And once you figure that out, you just find out the file size for that particular file. Then problem solved. Therefore, we need to go to the source code and find out how the request data structure is defined. And as you could see here, Polly has already looked it up for you. It's in here, net/http request.go, and in between, line 108 to 325. So that's go here to the source code. And I'm copying that and just, Googling the source file. Yep, request.go right here. And that's clicking to that. That should take us, there we go, the request.go source file. And I'm just going to use the browser's find function to go down, to the line 108 where the request structure is defined. So a lot of these lines are what? The comments. Okay, so it's to explain what each of the field means. So first field is called the method. Okay, and it's defined as a string data type. So this method here is to store the HTTP method, the first token in the command line. So be 3-character string if it's get. It will be a 4-character string if it's post. Right? So second field, if you read along, you'll see the URL is right there, the second field. All right, so URL, but it's actually this data type, a pointer to small URL dot capital URL. All right, so one will have to actually find out this data type, okay, somewhere defined in the source code as well. Okay. Let's go down a little bit. The third, in the command line, first token is the method, second token the URL, and what is the third token? The version of the HTTP. So proto here, okay, is the first field in the third token defining the string there. So HTTP /1.0, for example. Okay, so the whole string there will be stored in proto. The proto is also stored additionally as a pair of integers because the version is often 1.0, 1.1, 2.0. Okay, so the number before the decimal point and the number after the decimal points are also referred to as the major part of the version as well as the minor part of the version. So for 1.0, the major will be 1 and minor will be 0. Let's scroll down and we begin to see, hey, what's after the command line in an HTTP request? Yeah, the header lines. So header is another field in the request struct. This is where most of the header lines are stored. The type of the header field is a struct itself. It's the header struct. We didn't see the code of the header struct, but it's actually well explained in the comments here. So the header is a bunch of these mappings between a string and an array of strings. Now recall what these header lines look like. You have what? The name of the header line and then the values of the header lines. So you ended up having what? A bunch of these mappings between a string to an array of strings, because the name of the header is a string. Values are a whole bunch of these strings as well. Okay, so given the example above here, so this is a request containing 5 header lines. So the accept encoding gzip deflate is a mapping between accept encoding a string, gzip a string, deflate also a string. So this is an array of 2 strings. So the accept encoding header line is a mapping between a string and an array of strings. Similarly, for the accept language header line. Now, foo is the name of the header line. Bar, the value of foo. F being small, OO being capital. There's another header line, which is also a foo, but the OOs are small. Now, in Golang, HTTP requests header names are casing sensitive. So F big O, F small o, they are actually classified into the same header name. So in the header field, it will be just one string, FOO, capital F, small oo, and then 2 values, bar and 2. Okay. Now, in the header field, okay, the first string here indicating the header name will always keep the first character capital. So A and E are capital. A and L for the second header line also capital. Foo, yeah, F being capital. All right, so the first character of the words will be kept capital. That explains how these 4 header lines are stored. What about host being example.com? Yeah, this is quite interesting. The host header line is actually stored as a field itself. So request structs has a separate field called host. That is also a string that is just to store example.com. There are other fields also a bit special. Content length is also a header line, but it's a separate field itself. If we scroll down, you see right there, content length is a field itself, although it's a header line. And it's now an integer of 64 bits, so it's to store the data size. Further down here, you see host. Yeah, it's of type string, so this is where the example.com is stored. Now with the knowledge about the request struct, we can now go back to the example code here. So what we're doing here is to call the re-request API defined in net/HTTP. What it does is to take messages coming in from the socket, right, and parse it automatically and generate the request object. And the REQ here is the variable storing that object. And we now know the struct of that object. So we see req.host should be referring to the web server the HTTP request is going at. And req.method here should be giving us what? The method in the command line of the HTTP request message. Now the only line that is still not quite clear for you is just this. The last FMT printf. So what we're printing here is the value of the user agent header line. So user agent, and this is an API associated with the request object. So inside the request struct, we define the fields of the request object. But outside of that struct, there are also a number of these APIs defined for the request object. So if we go back to the source code, so this is where we were. Yeah, host is a field in the request struct, and which stores the host name of the web server the request is going at. So if we scroll down, we'll see other fields in the request struct. Okay, trailer, remote address, request URI, TLS, cancel, etc. CTX, it's also a field, okay, and it's of a spatial data structure itself. And finally, the end of the request struct. Okay, so inside the request struct, essentially a bunch of these fields. Okay, some of the fields very simple, string type, integer type, but some of the fields more complicated. Okay, and after the request struct, we begin to see a bunch of these APIs defined that associated with the request objects. Okay, so context here is to return. The CTX field value of the request R here. Okay, so R here, yeah, is just the request. So it's actually returning request's CTX field value. So we go down further. With context is yet another API associated with the request. Similarly, cloning of a request, proto at least of a request, and finally here, user agent. It's an API also associated with the request. What it does is to simply return request's header field. Okay, and by calling the get API defined for the header struct. And what it does is to do this. Search through all these mappings between the header name to the header values and get the values for the header name user agent. So essentially, user agent API here associated with the request object is returning the value of the user agent header line. Hey guys, look to the left. This is already what? Line 406. And we started from where? Line 108. Without you knowing, yeah, it took us some time, but we have explored 300 lines of code already. We know what are the fields in the request struct, right? We also learned there are actually some APIs conveniently available to allow us access to some of the values in other part of the HTTP request messages. What you need to do next is just to explore further. And let me take you back to the description of PA7. So what Polly has demonstrated in the past 10-ish minutes or so is to show how she discovers ways to access method in the HTTP request messages. And for example, the values of the user agent header line. What you need to do now is to explore further. Okay? Look for ways to access the token values required for the assignment, which is what? The URL field, that is the second token in the command line, and you need to find out the path name and the file name, so that provided these together, you could see in the file system whether the file does exist. If it does, tell the file size. If it doesn't, print file not found. Taking on the assignment, this approach is going to take some time because you're reading source code there. But the thing is this, it's also good investment because after some exploration, you will know the request struct very well, the associated APIs very well. So if you need to write another program that accesses HTTP request messages coming in from a socket, your code can be very brief. The effort is usually just very incremental. So the amount you need to spend next time is very short. And gradually, it's not going to take much time for you to find out what is the specific values you're looking for to process these HTTP request messages. And you know what? You don't really need to memorize the HTTP request message format, because by calling request, that is already done for you. You just need to know the request struct and the APIs, okay, and the related structs. Taking on this assignment, this approach is going to take you some time, yes, because you're reading source code that you are not familiar with. But the thing is that the more you try taking this approach, your knowledge builds up. So by the time you know the request struct really well, the associated API really well, when you need to write yet another program to access specific tokens in the command line or specific value in the header line, it's going to be a piece of cake for you, and the code is going to be very brief. Okay? You don't need to memorize HTTP request message format anymore, because all you need to do is just to call read request. Okay? So this is an approach that requires time early on, but things go easy and quick afterwards. So that was the exploration. How do you like that? Some of you might hate it. Okay, I actually, honestly speaking, I don't like reading others' code. But I have to say that Golang source code is actually pretty well documented. It's more enjoyable reading it. All right. Now let's go over the second approach. If that actually frustrates you, definitely.
The second example is
try the second approach.
So what we'll be doing here is to read the HTTP request coming in from the socket one line at a time, and then interpret these lines based on our knowledge of the HTTP request format. Now let's start the file, stringrequest.go. So we'll copy the entire block of code here into the .go file. Now, if you see in the main function, right, so we are printing launching server, we are starting the listening socket, and here is to wait for the client to dial up to create the data connection. And this is to wrap the socket that's opened around as a reader, so that in this for loop, we can begin to read using the read string. And so read string using \n as a parameter that is saying that we will read one line at a time. And that line is actually stored here in REQ. Okay. So the if condition here is checking whether the REQ is simply a pair of \r and \n. Now, allow me to explain. In HTTP request and response messages, each line will always end with what? CR, cartridge return, and LF, line feed. So \r is the cartridge return, and \n is the line feed. So an HTTP request messages very oftentimes ends with what? An empty line, which contains also just \r and \n. So this if condition is to check. If this is the last line of the HTTP request, then we exit the for loop and terminate the program. Otherwise, we go in here. Tokens being assigned as string.split. Okay. And string.split takes in two parameters. REQ, which is what? The line we just read. Okay. And then the delimiter. So we're using space here as the delimiter. So that line there, if there's space somewhere here, there, all the words in between, okay, the spaces will be isolated, singled out, Okay, and the output of all these words is going to be stored as an array of tokens. So tokens here, okay, will be walked through using this for loop. Okay, so for all I in the range of the token array, just print the value stored, okay, in that particular entry in the array. So what I'm doing there is, given a line, separate the words by the space, print each of the words out, and that's essentially everything in the example. Now let's go ahead and execute string request.go. So type up go run string request.go, and we're going to see launching server, and then the server is going to be waiting. On the client side, that's curl an arbitrary object on the local host. Okay, so curl 127.0.0.1 and the port number. Quickly, you see the curl responding saying, hey, empty reply from the server. Indeed, string request.go there is not sending anything back. And so the client side, you see quickly go back to the prompt. But on the server side, we'll see. After launching server, yeah, we're reading one line at a time, right? And splitting the lines into tokens separated by the space. So we see get slash http/1.1. So those are the 3 tokens in the command line of an HTTP request message. We see 3 more lines, okay? The host header line, the user agent header line, and the accept header line. So you see also here that the curl I'm using is version 7.64.1. Okay, so that is the user agent accessing the server string request.go. Now allow me to demonstrate. So let's go run string request.go. All right, so the server is launched, and that's curl localhost, and pollys server is always running on 11999. And let's see, there. We see curl saying empty reply from server and back to the prompt. And on the server side, we begin to see the command line showing the 3 tokens in the command line, the 2 tokens in the first header line, the host header line, and then user agent header line, and then the accept header line. Now, for your assignment, of course, taking this approach, then you will need to further process this particular token, which is the URL, and so that you find out the path name and the file name, and you look up on the file system and see if the file does exist or not. Okay, if so, print file size, otherwise print file not found. Okay, one last bit Polly needs to explain is just string star split. Okay, from the code walkthrough earlier, you might see already roughly what it does. Yes, it is a really nice API, allow us to split an original string into substrings. And that API is defined in the strings package. I know that some of you have already started using the strings package, but some of you might not. So in the package, it defines a number of these APIs, allow you to, for example, extract a substring from the original string, or concatenate strings together, things like that. And split here is allowing us to split an original strings into a number of substrings. And that is done by giving one parameter, the original string, and second parameter, the delimiter. Okay, so if we give space there as delimiter, then we will split the original string into substrings separated by the space. Okay, and the output of string.split is just an array of these substrings. Once you're done implementing your PA7.go, you'll need to do the testing using a regular web browser, such as Chrome, such as Firefox, or simply a command line browser, CURL. Okay? And so you need to request some HTML file and see how the PA7.go reacts. Now, Now, feel free to generate your own HTML file of arbitrary size. Okay. Now, if you don't want to bother generating that file, you can actually curl pollys test HTML file. So that can be done this way to your PA7 directory. So by the end of this, you will see server-test.html being created in your PA7 directory. Now you may curl or Chrome or Firefox to this file, server-test.html, and see if your PA7 responds with the correct file size. Now let me demonstrate pollys PA7. All right, so PA7 server launched, and now curl 999, and that's request the testing file HTML. There. Curl says empty reply from server. Yeah, because PA7 does not demand you to send anything back to the client, but PA7 demands you to tell what the file size is if the file exists. So PA7.go there is responding file size 2122. All right. Now let's try to curl a file that doesn't exist. Yeah, just the server. Okay. There. All right. Let's see. So that file does not exist. So the server side here prints file not found on the server side of terminal. So not sending any messages back to the client. And that's it. So the PA7.go poly demonstrated earlier is implemented taking the string request.go approach, which means I'm reading the text coming in one line at a time and then try to interpret where the URL is and then fetch the path name, file name, and then find out the file size. Poly implemented also a version of PA7 such that it's taking the simple request.go approach, which is to do what? Re-request, and then try to find a way to access the URL and particularly the path name and file name, and then get the file size. So let me demonstrate. Go run PA7 HTTP. All right. And then let me curl the same thing. Yeah, server launched. Server test.html. There. It returns the file size 2122. And now that's request an HTML file that doesn't exist. Test.html. Oh, test.html actually existed. Interesting. Okay, then let's do t.html. There, file not found. Okay, just to confirm. Server test. Yeah, that's the size. Test.html. Does it exist? Oh, okay, so it exists and it's the same file. All right, so yeah, working.
All right, so that's all for today. Poly's PA7HTTP.go is only 734 byte long, while the PA7.go is 2A something something bytes long. So you see that taking the HTTP package approach, the code size is much smaller. Source file is much smaller. All right. Good. So that's all, and perfect timing. Good. You're off to go, unless you have other questions you want to ask. I'm going to stay on for just a bit longer, maybe 5 more minutes, in case you have any questions. Good. Go get lunch. Good, so that's all for the string.